Good afternoon. Welcome to the second session of NVMSA. And I'm the session chair, Yizhong Chen from National China University. In this session, we have three presentations. And the first two presentations are in person, and the third one is online. So let's welcome our first presenter, Professor Yupei Liang from National Zhongzheng University. Okay.
Thanks for the introduction of the chair. And good afternoon, everyone. My name is Yupei Liang, and I'm glad to be here to share our research result with you. In today's presentation, the title is Minimizing Edge of Information of the Non-Volatile Random Access Memory-Based Intermittent Systems. This is today's outline, and I will introduce the system architecture of this work in the introduction section. I will explain what is the multi-level run of the non-volatile random access memory and introduce what is the edge of information in the background section. And then I will point out our motivation and introduce our method, which is called MASA, and show the evaluation and conclude this work. Okay. With the development of the Internet of Things, there are many applications widely used in the world, such as environmental monitoring, for example, the air pollution detecting or forest fire detecting or traffic detection. In the past, the trouble of these applications is how to charge the small devices in these systems. Luckily, recently, the energy harvest technology is gradually mature in the world. So the small devices in the IoT system can be self-powered supply levels that can harvest energy for the environment, such as solar power, wind power, or water power, and so on. And because they may be power failure if the power is not harvested is not enough. So they can equip the non-volatile random access for temporarily storing the data before the power failure happens. So with these two technology, we can build a system called intermittent system. So why is the system like this called the intermittent system? Because the small devices in in such system may be run the action or the program runs on it may be intermittently exclude because if the power is not enough, the program on it will be permanent. If the power is enough, the system will be running. So the system may be like this. There are a lot of sensor nodes spread all over everywhere, and because of the limitation of the transition distance, so several sensor nodes will transmit the data to a transmitter, and the transmitter will processing the data and determine which data should be sent to the controller. So such system and so this work we target on such systems, and let me introduce our system architecture in detail. This is the simplified system architecture in our work. As I mentioned previously, there are several nodes nodes and they are self-powered. They can harvest energy from the environment. And there is a transmitter between the nodes and the central controller. And this transmitter also self-powered device. And this transmitter, because this transmitter has to determine which data should be sent to the central controller. So it equips a non-volatile random access memory-based buffer for temporarily storing the received data. So this is our system architecture. And in this work, we will discuss how to minimize the edge of information in such system. So let's introduce two important technology in this work. So the first one technology is called multi-level write of NVRAM. So let's recall the advantage and the disadvantage of NVRAM first. The advantage of NVRAM is high cell density, non-volatility, fast read performance, low idle energy consumption, and bioaddressable. So because it is bioaddressable and high cell, because it is bioaddressable and non-volatility, so it is very suitable for the intermittent system. But it also has its disadvantage, such as the write cost. The write energy cost is much larger than the read energy cost of the NVRAM. And the other disadvantage is the some of the NVRAM suffer from the resistance drift. So why is the resistance drift? The resistance drift is a phenomenon that the resistance will be changed after a while. For example, this figure shows the MLC NVRAM how to distinguish different bit patterns. They usually divide the resistance into several states by the guidance. If the resistance in this area represents 1,1 as a bit pattern, and the resistance in this area we call this bit pattern is 1,0. And between this state, guidance is to protect the resistance drift phenomenon. But if the resistance drift over the guidance, the data representation will be wrong, so that the NVRAM usually guarantee the data correctness within a time interval, and this time interval we call it the retention time. So, but although we can see this resistance drift disadvantage, but some researchers find that if we need long retention time, we can add more energy consumption or and consume more time to program a cell. And if we need short retention time, we can use less energy and we can program the cell faster than the long retention time. So if we can use this properly, we can save the energy in the system. So that if we can predict the data lifetime, we can see this disadvantage chance to provide a feature that called the multi-level write mode. Why is the multi-level write mode? In this work, we divide the writing mode to two modes. First is normal write. The normal write provides longer retention time, but it should consume more energy, and also it will cause more program time. And the other is light write, and light write can retain much shorter than the normal write, but it can save energy and also use the less time. Okay. Also use few time. So in this work, we will use this multi-level write to further reduce the energy consumption in the intermittent system, because we all know the intermittent system, the energy in the intermittent system is very variable resources. On the other hand, I will want to introduce what is the edge of information. If we see the term edge of information, we can imagine that is indicator for us to help us to determine this data is fresh or not. And the formal definition of the edge of information is, can be seen as on the slide. The edge information is defined as the time is gapped since it lasted received update was generated. So this formal definition is hard to read. So we can, if we plot the relationship between the edge of information and the time of in our system, maybe like this. The x-axis denotes the time, and the y-axis means the value of edge information. So if data updates in time in the time, the edge of information will be returned to 0 immediately. So in this chart there are many isosceles triangles. So if we want to calculate the average edge of information, we can calculate by this, because the area of triangle can be calculated by the timing. The base can be calculated by timing the base 1/2 of the height. So the base and the height are equal. So we can calculate the average AOI like this. EIJ is the base length and also the high length. And it is half, and because we are calculating the average of AOI, so we need to divide the time interval is gapped. Okay. Sorry. So in our system architecture, we would like to keep the average edge of information lower to make sure the data in the system is fresh. So the goal of this work can be divided to the two goals. The first one is to use the multi-level writing mode to further reduce the energy consumption, and the second one is to reduce the average edge of information. And why we have to design the system for these goals? Because the traditional first come first serve cache and buffer replacement policy is not consider the edge of information, and also not consider the energy consumption of the intermittent system. For example, I will show the motivational example in the following slides. In this example, we have 5 nodes and with 1 transmitter, and this line is the time interval that each node update data. That means the transmitter receive the data at this time. For example, at time 10, the transmitter receive data from node 1. So, and in the right of the slides, this is the NVRAM-based buffer in the transmitter, and there are only 3 locations for the 5 nodes. Okay, so at the time 10, the node 1 sent to the transmitter. So because now the buffer is empty, so the node 1 can be stored in the buffer. And at time 12, the node 2 comes, so the because there are still empty locations, so the node 2 can be right into the buffer. And then until the time 13, because there are the buffer is full, so the node 4 has to choose a data to be replaced. So because we adopt the first come first serve policy, so we replace the node 1 in the buffer. So the node 4 can be right into the buffer and the node 1 just discussed. Okay. And after some updating at the time 12 and 26, the transmitter is harvests enough power to transmit the data. So the transmitter will transmit these 3 data to the central controller. And then the buffer will be empty again. And at time 27, the node 3 comes to the transmitter, so the node 3 can be right in the buffer. After a while, at time 38, the transmitter harvests enough power again, so these 3 nodes will be transmitted to the central controller again. So let's see the first and second time to transmit. The first time transmit, we send the node 1 at time the node 1 at the version of time 25 and the version of the time 20. Also, we also transmit the node 2 at time 24. And but the central controller only need the newest data of each sensor node. So the node 1 at the time 20 is the meaningless data. And second time transmit, we send the node 4 at time 35 and node 2 at 36 and node 3 at 37. And we can, as we can see the time interval, we replace the node 5, discard it, but it only updates at this time. So the drawback of the traditional first come first serve policy may cause some long updating interval data tends to be discarded, or they may send the meaningless data to the central controller. And on the other hand, the intuitive way to use the light write and novel write to save the energy is to write the data frequently updating in the light write, and the data updates not frequently updated by the normal write. But if we see the node 1, 2, 3, it's a short updating interval, and node 4 and 5 are long updating interval. But as we can see in the right figure, the node 4 at time 16 has been discarded, but we use the normal right to right length. So it might be waste. So that if we want to save energy, we can determine the writing mode by a simple threshold. We have to consider that the cache buffer replacement policy also. So to resolve this problem, we make an observation how to minimize the edge of information. So the observation is like this. These are two passes of the LOI accumulation. The axis is the time and the y-axis is the value of edge of information. And both of these two cases are nodes update twice within a t prime time. But the LOI accumulation shows the different result. The left figure, we calculate the average LOI by this equation, and on the other hand, the right figure, we calculate the LOI accumulation by these equations, and absolutely, this the left figure has the last LOI accumulation. So in our assumption, balance the update interval for each node is important for reducing the average edge of information. Okay, so with this observation and our motivation, we propose a method called MASA, which means the scheme for minimize average system edge of information. And the goal of MASA is to minimize the average LOI and design a buffer replacement policy aware writing mode decider. And the main idea of the MASA is to first is to predict the node behavior. So we design a updating intervals predictor, and then we want to balance the update frequency of the sensor nodes to prevent increasing the LOI rapidly. So we design a buffer management scheme. And the third one is to use the proper writing mode to further reducing the energy consumption. So we also design a writing mode decider. And all of these three components are in the transmitter in our system architecture. And these three components will help us to manage the buffer and also minimize the average system LOI in the whole system. Okay, so how to update the interval, as how to predict the updating interval. The intuitive way to predict the updating interval is to average all the past updating interval. But if we want to average the past interval, we have to keep every updating interval before transmitting, and then calculate the average for each node as the predicted updating interval. And also we need to record this predicted updating interval. But in the intermittent systems, this the small devices usually a very small embedded system, so the space overhead in such systems should not be very large. So we don't want to use this way. Instead, in MASA, we adopt a predicting factor alpha to predict the updating interval. How to predict the interval that we use this formula, which is the next update interval equals to 1 minus alpha times current interval to plus alpha times historical predicted update interval. And with this equation, we can predict the updating interval without keeping this table. Instead, we can only keep these two information of each node, that is the historical predicted update interval and the last update time. The last updating time is used for calculate the current interval, and the historical predicted update interval is the last predicted updating interval. So with these two information, we can calculate the next predicted updating interval by this equation and update the table. So this way can significantly reduce the space overhead. Next, how in our buffer management scheme, there are two main ideas. The first one is duplication check, because in our motivational example, we know that the system only needs the latest version of each sensor node. So if the data comes to the transmitter and it has the old version, we can just replace the old version of the data. And the other one is updating frequency balance. This idea is motivated by our observation. So we want to balance the update frequency of each node for avoid LOI increase rapidly. So how can we do this? Is besides the two information we keep in the last component, we add a bit flag for each node in the transmitter, and this bit flag will record whether the node has been updated last time or not. So if the bit flag is 1, it means this node has been updated less wrong. So if the data comes and the buffer is full, we tend to replace the bit flag with 1 because we want to update the data which is not updated last period. So this is the flow chart of our buffer management. First, we will check this data has the old version. If yes, replacing the old version directly. And then if not, if the buffer is not full, just writing the data to the buffer. And if the buffer is full, we check the bit flag. We would like to replace the data which with the bit flag, which is the bit flag is set to 1. Okay, so the next one is how to use the multi-level writing mode to further reduce the energy consumption. In this work, we have two modes of writing, which is normal write and the light write. And normal write has longer retention time, and the light write has shorter retention time. So main idea is to using the light write if the data is frequently updated and tends to be repressed. So we can use the information keeping by the updating interval predictor and the buffer management scheme. So in detail, we check the bit flag. If the bit flag is 1, it means this data tends to be replaced. So we use the line write to the data, and then the last check is if the data with the shorter updating interval, we use the line write mode. But if the data has the longer updating interval, we use the normal write. Okay, so let's see our evaluation setup. Okay, in our evaluation,
The rest of the presentation, can you wrap it up really fast? To take some important factors.
Okay, so because of the time limitation, so I just show the experimental results. So in this experimental results, we show the energy consumption of the three data sets, and the rightmost bar is our proposed method called MASA. As we can see in every data set, we can reduce about 30 to 40% energy consumption. And the other experimental result is the average of LOI, and also is similar to the result of the energy consumption. We can reduce the average LOI about the 35%. So let's conclude this work. In the proposed MASA, we propose an LOI-aware buffer replacement policy, updating interval predictor. Also, we're using the multi-level write to further reduce the energy consumption. And compared to the other scheme, we can save the 35% and 33% energy LOI and the energy consumption respectively. So that's the presentation of that's the end of my presentation. Thank you for your attention.
Thank Professor Liang for her exciting presentation. So due to the time, because we have 2 minutes late, I think we can take the question in offline. I think Professor Liang is more than happy to take your question offline, right? Okay, so let's our second presenter, Mr. Chen, right? Okay, so here is our second presenter, Mr. Liang Qichen, right? He is from National Cheng Kung University, and he is right now a master student, right? Okay, so let's
Hello everyone, I'm Liang Qichen from National Cheng Kung University. This is my pleasure to introduce my work, RNA sequence quantification, on processing memory architecture, observation, and characterization. In this work, we use the processing memory-based software to have an observation on emerging processing near memory product. Okay. Today, our talk will be organized into following sessions. And let's move on to introduction first. This is the data access pattern of general application and data-intensive application. In the past, most of applications perform very well on traditional architecture. Like the blue line, it only requires small amount of data during computation. However, some emerging application needs lots of data for computation during runtime. Like the red line, it needs more data than cache can hold. For example, neural network, genome sequencing, and graph processing. Because of the small size of the cache, there are a lot of opportunity data movement between CPU and memory, and it becomes an overhead in traditional architecture. So there is a solution called processing memory. Processing memory, which means we need to process the data near or in the memory device to avoid frequent data movement between CPU and memory. And there are two types of processing memory. The first one is processing using memory, which means the data can be processed directly by memory circuit component. For example, IEEE crossbar array is usually adapted to neural network computation. The other one is processing near memory, which means we keep the small processing units into the memory device or close to the memory device. For example, a main DPU is a group of processors inside a DRAM chip. And compared to processing using memory, processing near memory is more flexible because we can totally manage our workflow in software layer. And the upmain DPU is an emerging processing near memory product. So our objective of this work is to enable a strong understanding of upmain DPU. In the background session, I will introduce upmain DPU and RNA sequencing algorithm. Here we are going to introduce upmain DRAM processing unit, that is DPU. Each DPU can be seen as a small processor with 24 hardware threads, or we can call it hardware thread tested. Each DPU contains 24 kilobyte IRAM to store instruction information, and 64 kilobyte WRAM, which is a cache in a DPU, and 64 megabyte MRAM, which is a DRAM bank in DPU. And there are 8 chips in a DIMM rack, and there are 8 DPU in a chip. So there are 64 DPU in each rack. And the way to communicate with DPU is transfer the data from host DRAM to PIM DRAM through the host DPU. And the way to use the DPU is first transfer the command and input data from host to DPU by transfer function provided by upmain SDK. And then we launch the DPU, which means we execute the DPU program. Third, after the execution, we can get a result from DPU to the host by transfer function again. And there are many restrictions on the use of the DPU. It will require many considerations in our software design. First, CPU access DPU MRAM only by transfer API, not the RAM memory access. Second, the communication granularity is a rack instead of a single DPU. Third, data transfer and DPU execution cannot work concurrently. This means more data transfers, more DPU idle time. And there is no data sharing among DPUs. Each DPU can only access its own MRAM. If the data sharing is necessary, the data have to send to the host CPU and then to others DPU. Next, I will introduce RNA sequence quantification. Quantification is a way to know the quality of a set of sequence. And the most time-consuming step in quantification is read alignment. There are two inputs for read alignment. The first one is read. Read is a set of shorter sequence. The other one is transcriptome. Transcriptome is a correction of long reference sequence, and each reference sequence is transcript. The output of read alignment is similarity class. Similarity class is to record how many reads is most similar to each transcript. Quantification requires we iterate over all reads and compare each of them to every transcript. So next, I will introduce a software can finish this step in an efficient way. This is Callisto, one of famous quantification software for short reads. The way Callisto works is first build a transcriptome to Debian graph. In the graph, each node is a k-mer, and the whole graph is stored by a hash table. In hash table, the key is k-mer, and the value is k-mer's corresponding contig. Contig is mean an overlap between sequence, and k must mean all length k substring in a sequence. And there's a sequence data structure contig array to record in which transcript the contig appears. This is an example. There are 3 transcript and 3 contig in graph, and k-mers in contig 0 are AAT, ATT, and TTA. These k-mers corresponding contig are all 0 because these k-mers are all belong to contig 0. And contig 0 in contig array has 3 values, T1, T2, and T3, because contig 0 appears in this transcript. The following is an example for input read. The read will be cut into k-mers and hashed to the labeling graph. And we can note the corresponding contig from this hashed k-mer. And then Callisto can get the information by contig array and then do the intersection. For example, this read is more similar to T1 and T2. And then finally, Callisto can go to update the similarity class. The motivation of our work is usually sequencing the large number of reads is about 10 million to 100 million. So processing memory is the possible way to increase the throughput of application. However, there is no many work show the state of the art. Sequencing softwares can be accelerated by augment DPU, and also sequencing on augment may have some concerns like DPU constraint and frequent data movement between CPU and DPU, or DPU-based programming issues. So we choose Callisto, a RNA sequence quantification software, to be a case study understanding the characteristic of sequencing augment. Next, we'll move on the implementation of our work. In this slide, I'm going to show you our implementation of DPU-based Callisto. In the host, there are 2 threads. The first one is communication thread is responsible for read transfer and restore transfer. The other one is working thread is responsible for intersection task. The reason behind we allocate 2 different threads in a host is because we want to reduce the idle time in both DPU and CPU, and we want to make DPU and CPU can work concurrently. And this is the data structure in Callisto. That is a hash table in a contig array. The first step is we broadcast the hash table into the DPU set. All DPU in the DPU set will get the same hash table. The reason behind why we only transfer hash table instead of whole data structure, including hash table and contig array, is because of the limited size of DPU NVRAM. The second step is communication threads send the read packet to the DPU. Each DPU will get a different reads. This means we can process a lot of reads at the same time. The third step is we have a DPU execution. Reads will be cut into k-mer and matched by hash function. After the execution, each DPU will hold their local result in their NVRAM. The fourth step is communication thread get a result from the DPU and push the contig ID into the host. And immediately, communication thread will go back to the second step and send the next packet to DPU. At the same time, a working thread will get contig ID from global queue and then do the intersection. The implementation of DPU-based Callisto is only a basic workflow or a basic design. There are still some design challenges when we are facing different workloads. The first one is the size of large hash table. Hash table can be sometimes larger than 64 megabytes, which is a size of DPU NVRAM. To deal with the problem caused by large hash table, we have 2 policies to manage our workflow. The first one is replacement policy, and the other one is split policy. The second challenge is how to resolve the programming issues caused by limited size of DPU WRAM. WRAM is the cache in DPU, and the testlet in execution will share the space of the WRAM. This means more number of testlets in execution, the less WRAM space each testlet can be allocated. To address the issue, we have two different cache mechanisms, long cache mechanism and 128-byte cache mechanism. And let's move on to the first design challenge. The large hash table is divided into k subtables. Replacement policies requires all DPU to get the same subtables at the same time. For example, there are n DPUs in this case, and these n DPUs all got table 0 first, and host transfer and read into DPUs, and after the first DPU execution, we transfer table 1 into DPU and then execute the DPU program again. Table transfer and DPU execution have to be repeated k times because we have to ensure all subtables are searched for each read. The advantage of these policies is we maintain the parallelism of the design because the numbers of process reads is only depends on the numbers of DPUs. But the trade-off is we have a lot of DPU execution and a lot of table transfer. The second solution is split policy. The large hash table is divided into k subtables too. However, this time we evenly distribute the subtables into DPUs. This means all DPUs do not get the same subtables at the same time. And the split policy duplicates k copies of each read and transfer k copies into k DPU with k different subtables. Different from replacement policy, split policy is try to avoid frequent data transfer between CPU and DPU. So we can see there's only one DPU transfer and one table transfer, whatever how many subtables we have. But the trade-off is it leads to the degradation of the parallelism degree. This slide shows the experiment of comparison between two policies. The figures are the breakdown of program execution time. The key difference between two policies is that table transfer time in replacement policy is much more than in split policy. This is the comparison of overall performance. The yellow bar is the execution time of DPU-based Callisto, and the blue bar is the execution time of CPU-based Callisto. The first observation is DPU-based Callisto is less efficient than CPU-based Callisto. So we can get a small conclusion from this observation. Frequent data transfer is an overhead in DPU system because there is many table transfer in replacement policy. And we have another observation. DPU-based Callisto with split policy does not perform very well in small data set. But its throughput exceeds CPU-based Callisto very much in big data set. So we can get another conclusion from this observation. Unmanned DPU system is a good material suitable for large data size workloads. Let's move on to the second design challenges, DPU-based programming issues. The workflow of general DPU program is that data have to move from NVRAM to WRAM, and after data is processed in WRAM, it have to be written back to the NVRAM. And the testlet in execution will share the space of the WRAM. In this case, we have two testlets, and reads are being moved from NVRAM to WRAM. During the read alignment, long cache mechanism try to keep all resource in the WRAM to avoid the use of mutex lock. In this design, we don't need any mutex lock. But however, in order to keep all resource in the WRAM, the size of the cage have to depend on the number of cameras, which is usually very large. So it leads to an issue, which is we can only process a few number of reads in a DPU execution. Another design is 128 byte cache mechanism. We reduce the cache size into 128 bytes. The reason behind the size is because existing benchmarking research shows 128 bytes is an efficient data size for data movement between WRAM and NVRAM based on the hardware architecture. In this design, we have limited size of cache, so a multi-slot is required. However, because the cache size is a constant size, so we can increase the size of the read packet. This slide is a comparison between two different cache mechanisms. We can see 128 byte has a higher throughput than the long cache mechanism. So for DPU program, 128 byte cache mechanism is more efficient. And they have another observation. We can only process 20 reads when we use long cache mechanism. But when we use 128 byte cache mechanism, we can process 800 reads. So there is a conclusion from this result. WRAM is expensive. We have to design the workflow very carefully during the DPU-based programming. Finally, this is the conclusion of our work. First, we implement DPU-based Callisto and put the source code on GitHub to help the communities more understand the DPU-based programming. Second, we have a lot of experiments and to show the trade-off between program performance and DPU constraint. Finally, we give some suggestions and consideration of DPU programming, like frequent data transfer is a potential overhead in DPU system, and WRAM is expensive. We should use WRAM with fine-grained design in DPU programming. This is my talk today, and thanks for your listening.
And thank you for the amazing presentation. So is there any questions? So we have 5 minutes to take questions.
Your implementation looks like only upload some jobs into DPU. And are there any new ideas in the implementation compared to original Callisto?
Okay, here's a good question. Our implementation is just offload some job into DPU because the objective of our work is try to have some observation and characterization on advanced system. And in the future work, we will try to design a new software based on the observation and conclusion based on this work. And the software can maximize the strength of the DPU system. Thank you.
There's a question. Then how can you know cluster is suitable for PIN system? That is, for this code is a very fun software.
Do you mean how can I know the Callisto is a good case study for admin system, right?
Yes.
Okay. Because first we know there is not too many complicated computation in Callisto, and Callisto needs a lot of data for read alignment. So we think Callisto may be a memory bound application, and we have a backup. This is a loop-fly model analysis from Intel Advisor, and the breakpoint is the Callisto. We can know Callisto is in the memory bound region, so we can ensure Callisto is a memory bound application. And usually, memory bound application is suitable for processing memory-based architecture. So the Callisto is a good case study for the admin system. Thank you.
Thank you.
So is there any other questions? Okay, so I have one question for you. So how do you do the partition of jobs between CPU and the DPU.
Partition the job.
Yes.
You say our implementation, right?
Yes.
Okay.
Because I didn't see you mention this part of work, right?
Okay. Let me go to the slide of our implementation.
Okay.
In this work, we offload the alignment part into the DPU,
Okay.
and the intersection part is in the host.
Okay.
And then we use two different threads to make DPU and CPU can work concurrently.
Okay, so how do you make sure they can work concurrently? Because there should be some kind of a synchronization or things like that to make sure there's no contention or something like or any delay like that. Right? So how do you implement this to make sure that there's a certain concurrency?
Or the concurrency is provided by Admin SDK. We
Okay.
just call their function and execute a DPU program.
Okay.
Yeah.
Oh, so it is very similar to GPUs, like
Yeah. Like
a
a
library, so you can call the API, the synchronization
Yeah,
API
yeah.
to make sure that everything can work.
the DPU is like a accelerator.
Okay, thank you. Okay, thank you very much. It's very interesting. Okay, so so we still have a little bit of time. So if you have any questions, is there any questions? No? Okay, I think we can move on to the third presentation. Right? Okay. So the third presentation, the third presenter is online, right? We will play the video first, and then Mr. Lee is online already. He will take questions from us. So let's play the video first. Thank you.
Hello, everyone. I'm Cheng Li from East China Normal University. Today, I'm glad to be here to introduce our recent work, Latency-Aware Page Migration for Read Performance Optimization on Hybrid SSDs. Now, let's begin from the introduction. NAND flash has experienced significant development during the last decade, from SLC, MLC, TLC to QLC. The increasing density comes with the problem of performance and endurance. To hide these downsides, consumer SSDs are widely designed with a hybrid architecture, combining SLC and high-density flash memory. By utilizing SLC blocks as the cache of QLC blocks, the whole system throughput can be significantly improved. They work well with large capacity at low cost. However, some works found that the variation of read latency is becoming more and more evident as the storage density increases. The user's experience would be greatly affected once hot data happen to be in high latency pages. Then I want to give a brief introduction on hybrid SSD. Hybrid SSDs have two regions with considerable performance discrepancy. SLC has a fast and stable read performance, but a small capacity, while QLC has large capacity but wide read latency variation. There are three typical data flows in it. First, read. The read path in hybrid SSD is complicated. It depends on the region where the page is located, and there are 5 different page types: SLC, Q1, Q2, Q3, and Q4. Among them, the SLC page has the best latency, while the Q4 has the worst latency. Second, write. All data will be first written to the SLC cache and be migrated into QLC blocks in trips once the free space of the SLC region is lower than a threshold. Third, migrate. This operation happens when the free space of the SLC region starts running low. Valid pages in the SLC region will be read to the DRAM cache of the SSDs and then be written to the QLC region. Now, let's take a look at the development of hybrid SSD. More than a decade ago, many work started to use fixed-size SLC as a cache of MLC to improve the write performance. Then, the size of SLC cache becomes self-adjustable. These strategies are designed for the write performance optimization. All this work focused on the mode switch of hybrid SSD and mainly addressed the problem of write performance and endurance from the SSD controller level. There are also some work targeted at the optimization of read performance on QLC. H20, a combination of OptiMemory and QLC, caches the recently accessed data in OptiMemory. Others propose to place frequently read user data on low latency flash pages. However, the caching strategies need actual storage mediums, and the internal relocation strategies needs SSD firmware modification. None of them pay attention to the variation of read latency on hybrid SSD. Then we studied the read latency characteristics on a QLC-based hybrid SSD. First, a test file is created on SSDs and read at once. Second, a large file is created to fill the SSD region, which will enforce the migration of the original test file. After a while, the same test file is read for 3 times. According to the data path, it can be inferred that the test file is located in the SSD region during the first round of test and in the QLC region during the last 3 rounds of test. To begin with, we focus on the average page latency. From the figure, we can clearly find that the SSD region has only 1 type of pages, while the QLC region has 4 types of pages, from Q1 to Q4. The average latency of the Q4 page is 4.2 times to that of the SLC page. 5 types of pages are discovered in hybrid SSD, and they exhibit wide difference in read latency. A simple solution to improve the read performance is to migrate the data in the QLC region to the SLC region. Page migration can be easily realized by reading the data in the QLC region and rewriting them. In the following migration test, we have a test file in the QLC region at the beginning. During the first migration, all the Q4 pages of the test file are migrated to the SLC region. Next, the Q3, then the Q2, and finally the Q1. In the end, all pages are in the SLC region. As more data are migrated to the SLC region, the high latency pages are gradually eliminated. Despite more migrations means better performance, it's worth noting that migrating the data from the Q3 and Q4 page is more rewarding. From the above test, we draw a conclusion that the migration of data from QLC pages can be effective in optimizing read performance, and it fits the problem of diminishing returns. Well, there are also some limitations. First and most importantly, the migration strategies works well only when the migrated page are hot-data. So the efficiency of this method mainly depends on skewed read-dominant workload. Second, page migration will generate the writes to SSD, which introduce Latency to the flash. The figure shows the migration ratio in the previous experiment. The more page types are migrated, the greater amount of additional read traffic is. Last but not least, this strategy may also be constrained by the read-write conflict. At high queue depths, the migration traffic can interfere with read operations and therefore offset the benefit. In the experiments, random 4KB requests are issued. With the queue depth of 16, we vary the percentage of reads 20%, 50%, and 100%. This figure shows the CDF of read latencies. With the increasing of writes, read operations are badly interfered and its performance degraded significantly. The workload characteristics and the flash peculiarities can limit the effectiveness of page migration, and aggressive migration may not be the best choice. Based on the above findings, we propose to optimize the read performance through page migration. However, there are some challenges to be solved. First, the worst migrating data should be determined. For example, code data is definitely not suitable for migration, since they may not be read after migration. In addition, the QRC page with a low latency is unworthy of migration because it has comparable latency than that with that of SLC pages. Second, a good migration policy will not only ensure an efficient page migration, but also minimize the system overhead. To overcome these challenges, latency-aware page migration is designed to identify the high latency pages with frequent reads. Then they are migrated to the SLC region. As a device-specific scheme, LAPM is implemented at the user space without violating the kernel integrity. It includes two components, a page candidate generator and a page migration module. The former component aims to find the worst migrating pages. It will consider the request history and the page type of hot data. The latter component executes page migration with a specific migration policy. Here is the page candidate generator. First, migrating all data will not always bring the best results. This is because it may introduce serious read-write conflict problem. To minimize the migration traffic, LAPM only migrates the hot data. Therefore, the hot data identification strategy is critical to LAPM. We adopt a classic hot data identification strategy, which will count the number of occurrences per read request and sort. It marks part of the request with a large number of occurrences at hot data and exclude the other parts. To make it more smart, the threshold for hot data identification is tunable, which depends on the user's need. In general, a higher threshold means a lower likelihood of migration and leads to less migration traffic. Specifically, we monitor for the first 30% requests of the task thread using block trees to record the I/O activity in the block I/O layer. The key information of every I/O request, such as logical sector number, sectors, and the directions for the hot data identification are extracted. Second, to further minimize the migration traffic, it's wise to only migrate the high latency pages such as Q3 and Q4. However, the attributes of a specific page is transparent to operating system, which is exclusive to the device. In order to get the accurate page attribute information for subsequent page migration, an offline detection strategy is proposed. We issued 4 KB single queue depth random read request to the hot data and determine the p type of each page by considering its latency. This figure clearly shows the process in steps. First, sort events based on the I/O count and identify hot data. Second, get path name and file extent using debug effort. Third, get p type of hot data through attribute detection. Fourth, decide the candidate page. From the results, we can find that the second page of test is Q4, while the first is Q1. LAPM choose the second page of the test of the file test as the candidate page and exclude Q1 and Q2. In short, the page candidate generator saves the worst migrating page according to the page hotness and page attribute information. Next is the page migration module. Traditional migration will migrate all hot data regardless of page type. Due to the little latency margin between the SLC page and the Q1 page, this kind of migration proved to be inefficient when a large request contain both Q1 and Q4. With the offline page type information, we can migrate the data in a finer granularity. It will migrate the slowest page and exclude Q1 and Q2. To further minimize the system overhead caused by page migration, multiple contiguous pages will be coalesced into a migration request. It's because fewer I/O commands means better efficiency. In short, LAPM will migrate the slowest page and exclude Q1 and Q2 pages, which strikes a balance between latency reduction and additional migration traffic. Next is a section of evaluation. The inter-QRC-based SSD is selected, and we use FL to generate a synthetic read-only workload, and we also select MRSR trace to simulate complex scenarios. In addition, we compare our work to 3 other strategies. Baseline is the existing architecture of most hybrid SSDs, which does not migrate QRC data to the SLC region. Read migration is an aggressive migration strategy, and the data will be migrated after the first read. Hot migration will migrate the hot page regardless of its page type. For synthetic workloads, we mainly focus on the impact of workload locality on read performance. There, 90-10 means 90% of reads hits on 10% of data. From the left figure, we can find that all strategies work well, and the more skewed, the better performance. The right figure presents the efficiency comparison, where efficiency refers to the latency reduction divided by the amount of migration. Although aggressive migration gains maximum benefits, it leads to diminishing returns. LAPM only migrated the critical data so that it's more efficient than its counterpart. Under macro benchmarks, we play MSR trees to add different Q depths to simulate complex scenarios. At single Q depth, LAPM reduced the read latency by 22% on average. In the case of 16L depths, the latency reduction caused by page migration becomes flat. This is because there are too many requests issued to the device at the same time. Take HM0 as an example. Read migration increase the average read latency instead due to that it's introduced serious read-write conflict. On top of that, we also present the read-write performance due to the interference of page migration. The write performance are affected in some way. From the figure, we can clearly find that LAPM outperforms its counterpart with the minimum performance overhead. In addition, the amount of migration traffic is also collected to showcase its advantage. LAPM consider the page attribute information and execute the data migration in a finer granularity. Compared with the HM0, LAPM reduced the migration traffic by up to 40% under USR0. Therefore, under different workloads, we always guarantee the minimum write traffic and cause little wear on flash memory. Here is the conclusion. In this work, we demonstrate the wide variation of read latency and explore the benefits and limitations of page migration based on an empirical study of a QRC-based hybrid SSD. We further propose efficient user-based migration strategies, LAPM, which can identify the frequently read pages with high latency and migrate them to the SLC region. We implemented LAPM and conduct experiments on real hybrid SSD. Results show that it can achieve encouraging performance at different Q depths. That's all. Thank you. Please feel free to ask any questions.
So is Mr. Lee turned on his microphone already? Yes, okay. So is there any questions? So we have 10 minutes to take questions. So is there any questions? Okay, so Mr. Lee, I have one question for you. Since that in your SSD, you can the SSD can be written utilizing the single level cell mode or the multi-cell level mode, right? So you're using the single level SLC mode. It would be more efficient, but it would also take more capacity of the SSDs. So is it possible to increase the percentage of garbage collection, things like that, when you're utilizing too much SLC mode?
Well, sorry, I didn't follow up. Could you please repeat it?
Sorry, can you turn on your volume a little bit? It's kind of a
Louder. Sorry, can you hear me?
yes, but it would be nice to be louder.
Oh, to be.
So we're trying to turn on the volume here too.
Oh, okay. I will turn it. I will fix it.
Okay, so I think here we have the maximum volume. So
Okay. Okay.
okay, I think this one is good. Okay.
Oh,
Right now it's
okay,
good.
okay. Yes, your question is the SLC will interfere with GC. This is your question. Is
Yes.
this your question?
Because when we're utilizing too much SLC mode, it may be good for the performance, but it would utilize too much capacity of the SSD, right? So it would be more likely to invoke the garbage collection process.
Garbage collection.
Yes.
Yes. So I will answer your question. First, our proposal is our design is designed to improve the rate performance. So for most workload, we choose read dominated workload. So there is a little possible to invoke the internal GC operation.
Okay, so so right now you're focused on you mean that you focus on evaluating the read process, the read
Yeah.
performance instead of
Yes.
the write. So there's no evaluation of this part.
And then we choose we can choose the hot threshold and admit a proper amount of data. So this is can avoid some additional GC operation.
Okay, thank you very much. Okay, so no other questions? Okay, I think there's no other questions. So I think this will conclude the second session. Okay, thank you for joining this session. Thank you.